And that's when I realized these ETA predictions aren't just some nice-to-have feature. We're talking about billions of dollars hinging on getting these numbers right.
Billions. You're saying a slightly off ETA prediction can actually impact a company's bottom line that much?
Oh, absolutely. Think about it. If Uber Eats consistently underestimates delivery times, customers get frustrated, cancel orders, switch to competitors. If they overestimate, drivers are sitting idle, wasting time and money. It's a super delicate balance, and the cost of getting it wrong is enormous.
Okay, I see your point. So we're talking about more than just customer satisfaction. It's about optimizing the entire logistics chain. What happens when these systems fail? What's a real-world example of an ETA prediction gone wrong?
Remember that huge snowstorm last winter? DoorDash ETAs were completely useless. People were waiting hours past the estimated time. Orders were getting messed up, drivers were getting stuck. It wasn't just an inconvenience, it was a logistical nightmare that probably cost them a fortune in refunds and lost business. The algorithms hadn't been trained on extreme weather events adequately.
Right. So a critical part of this is accounting for real-world unpredictability. Let's dive into the tech. What are the core components of the ML stack that power these ETA predictions?
At the heart of it, we're talking about a complex interplay of factors. First, you've got the historical data. Think about every single delivery ever made, the route taken, the time of day, the weather conditions, the restaurant's prep time, traffic patterns, driver speed, even the type of food ordered.
That's a massive data set. How do they even begin to process that kind of volume? Are we talking about petabytes of data here?
Oh, easily. And it's not just about volume, but variety. You've got structured data like order times and GPS coordinates, and unstructured data like restaurant reviews and driver notes. Companies like Uber and DoorDash use distributed data processing frameworks like Apache Spark and Hadoop to handle this massive scale. They're running on cloud infrastructure like AWS or Google Cloud.
Okay, data ingestion and storage is one piece, but what about the actual ML models? What algorithms are they using to crunch all this data and spit out an ETA?
This is where it gets interesting. It's not just one model, but a whole pipeline of models working together. At the simplest level, you have regression models predicting travel time based on distance and speed. But then you layer on more sophisticated techniques.
Like what? Give me some examples of these sophisticated techniques.
Well, for example, they use graph neural networks, or GNNs, to model the road network and predict traffic flow. Imagine each intersection as a node and each road as an edge. The GNN can then learn patterns of congestion and predict how traffic will evolve over time. Netflix uses similar GNNs to predict movie recommendations based on user viewing patterns and movie similarities.
Okay, so GNNs for traffic prediction, that makes sense. But traffic isn't the only factor. What about restaurant prep time? That seems like a huge variable.
Exactly. That's where the third component comes in, real-time updates and feedback loops. These systems are constantly learning and adapting based on what's happening in the moment. If a restaurant is running behind on orders, the ETA is adjusted accordingly. If a driver encounters unexpected road closures, the ETA is updated in real time.
So it's a continuous feedback loop. The model predicts, the real world happens, the model learns from the difference and adjusts. How do they handle the cold start problem for new restaurants with no historical data?
Great question. This is a tricky one. They often start by using data from similar restaurants in the area. They might also rely on initial estimates provided by the restaurant itself. As more data becomes available, the model gradually learns the restaurant's specific characteristics. It's a process of continuous refinement. Amazon deals with a similar cold start problem when recommending new products, using metadata and user behavior to make initial recommendations until enough data is gathered.
This sounds incredibly complex. So we've got data ingestion, sophisticated ML models, and real-time feedback loops. What's the biggest challenge in building and maintaining these systems at scale?
Here's where it gets interesting. It's not just about the algorithms or the data, it's about the infrastructure. Imagine trying to process millions of requests per second while also constantly retraining your models with new data. You need a massively scalable and reliable infrastructure to handle that kind of load.
So we're talking about things like load balancing, auto-scaling, and fault tolerance. How do they ensure that the system remains stable even when things go wrong?
Exactly. They use techniques like containerization, Docker, orchestration, Kubernetes, and monitoring, Prometheus, to manage the complexity. They also build in redundancy at every level so that if one component fails, another one can take over seamlessly. Think of it like building a bridge that can withstand an earthquake.
So it's not just about having the smartest algorithms, but also about having the right infrastructure to support them. What happens when the infrastructure itself becomes a bottleneck?
That's when they start looking at things like specialized hardware accelerators, GPUs, TPUs, to speed up model training and inference. They might also explore techniques like model distillation to create smaller, faster models that can run on edge devices. Google famously uses TPUs, or tensor processing units, to accelerate its machine learning workloads, gaining significant performance improvements.
Okay, so we've covered a lot of ground. What's the one thing that most engineers get wrong when thinking about ETA prediction systems?
The biggest mistake is thinking of it as a static problem. They treat it like building a model, deploying it, and forgetting about it. But the real world is constantly changing. Traffic patterns shift, new restaurants open, weather conditions fluctuate. You need to constantly monitor your models, retrain them with new data, and adapt to the changing world. It's like building a self-improving organism, constantly learning and evolving.
Okay, those are three solid takeaways: data quality, robust infrastructure, and continuous feedback. Anything else?
Yes, don't be afraid to start small and iterate. You don't need to build the perfect system from day one. Start with a simple model, get it working, and then gradually add complexity as you learn more. Think of it like building a house. You don't start with the roof.
Good point. Start small, iterate, and focus on the fundamentals. So, if you could sum up the key to building a successful ETA prediction system in one sentence, what would it be?
It's all about building a system that's not just smart, but also adaptable. A system that can learn from the past, react to the present, and anticipate the future.